Good morning, folks. How's everybody doing? Bright-eyed and bushy-tailed? Oh, that's helpful, actually. Okay. So today we want to talk about 6.5. We did 6.3 and 6.4 over the last couple of days. So today I want to talk about 6.5. But before we do that, are there any questions that have come up as you've worked on particularly 6.3? A fair amount of you have gotten pretty deep into 6.3, but not too much further. So as you worked on that, did any questions come up that you want to look at? Should I take that as a no?
A question like 9 on 6.3.
9 on 6.3. I'll have to check that. I think I know which one that is. Oh, yep. Good. That's one of the ones I was hoping to talk about. So let's say we've got an angle at 210 degrees. So 210 degrees is down there somewhere, where this angle theta is equal to 210 degrees. Now, I don't actually know what the sine of 210 degrees is, but we know it could be represented by this physical height h, right? That y value. So it's going to be some negative number, and it's going to be a negative number that represents that length. So what this question is asking in 9, it says, find another angle between 0 and 360 degrees. So find a different angle in the first rotation that has the same sine value as 210 degrees does. So another angle that has that same height for its sine value. Now, because that sine value, that h, is going to be negative, what other quadrant must we be looking at? What other quadrant is sine negative in?
Four.
Since we associate sine with our y values, it is absolutely also in 4. So we'd be looking for another angle down here that has that same height, that same y value, that same sine value. We just want to know what that angle is. Well, there's a couple of different ways we could figure it out, but one of the probably nicest is with what your text calls reference angles. So this big angle here is 210 degrees, but if I wanted to take just a little reference here, this little angle here, notice it's measured positively in its orientation, and it's measured from an x-axis. That little reference angle there, and it is technically called theta prime, if you're curious. But that reference angle, do we know how many degrees that reference angle is?
30.
It's got to be 30. Take the 180 away from the 210. This little angle down here is 30 degrees. Well, if it's supposed to make the same height as it does here over here, what must this little reference angle be?
30.
It must also be 30 degrees. Notice again, it's measured positively to a x-axis. So if that angle's got to be 30, that reference angle has to be 30. Could we figure out what that angle is?
Well, it has to be 330 because all the way around would be 360.
Yeah, all the way around is 360. So the angle of 330 degrees. Now, they're certainly not coterminal, but they do have the same sine value. The sine of 330 degrees is the same as the sine of 210 degrees. And there's no other angle in the first rotation between 0 and 360 that will do that. Now, are there other angles that are the same or that have the same sine value? I'm seeing a lot of yeses. Good. Anything coterminal to those is going to also have the same sine value. And this question is going to become really important when we start solving in chapter 7, because when we start trying to solve, our solving techniques are going to give us one of these angles, and we have to find all of the others. So we'll be given an answer like the 210 degrees and have to go, okay, if 210 degrees is an answer, and I'm talking about sine, then 330 is another answer. So they're kind of getting you ready for that. Does that seem reasonable? The problem then goes on to ask, okay, what about cosine? What's an angle where the cosine of that angle is the same as the cosine of our 210 degrees? Well, we know cosine is physically represented by that horizontal displacement. So that's our cosine of 210 degrees, is that blue length. And that blue length is going to be negative. So the cosine in quadrant 3 is negative. So what other quadrant must we look for the angle we wanted? What other quadrant is cosine negative in?
2.
Yeah, it's negative up in 2. So we'll be looking for an angle in quadrant 2 where the cosine value is the same, where that horizontal length is the same. And you might notice those sine values are going to be the same absolute value, right? One's going to be positive and one's going to be negative. But the cosines will be the same. So again, we want to figure out what is this blue angle. And all we know is it has to be symmetric to this 30-degree reference angle. Well, that means that this angle here has to be 30 degrees. Thus, what's that blue angle?
150 degrees.
150 degrees. Who asked that question? I didn't catch it.
Me.
Oh, Fernando?
No.
No?
Alec.
Oh, Alec over there. Okay, sorry. Alec. Did that make sense?
Yeah, it did. I just was having trouble visualizing it.
Drawing out a little circle is a really, really big help. Whenever I do these, I draw myself, a little circle. Makes a big difference. We also, of course, need to be able to do this in radians. So if we want to, say, find an angle in the interval from 0 to 2 pi, so we're in radians, such that it's, let's stick with sine value. Its sine value, oops, is equal to, let's say the sine of, what do I want? How about just pi over 4? Make it super nice. So find an angle in the first rotation such that its sine value is equal to the sine of pi over 4. Before we do anything, the sine of pi over 4, is that going to be positive or negative?
Positive.
Pi over 4 is in quadrant 1. Sine's positive in quadrant 1, so absolutely, it's going to be positive. What other quadrant has positive values for sine?
Quadrant 2.
Quadrant 2. Good. So before doing anything, we know the angle we're looking for has got to be in quadrant 2. Fair? But I am going to encourage you guys, and as I said, whenever I do these, I draw myself a little diagram because it's not a very good diagram, but that's okay. Because it keeps me organized. So again, when we're doing things like solving, if we find that pi over 4 is one of our answers when we solve and we're working with sine, we have to know, oh, wait, there's going to be another answer in quadrant 2 that has that same reference angle of pi over 4. If that little reference angle is pi over 4, what's this other angle?
3 pi over 4.
3 pi over 4. Is that horrible? I can try to make it horrible if you want. Now, why not? So let's change this to cosine of 2.3. So I'll give you a minute to try to do that. Find an angle in that first rotation such that it's, such that its cosine value is equal to the cosine of 2.3. What quadrant is 2.3 radians in?
Two.
It's in quadrant 2. Remember, that's pi radians. That's pi over 2 radians. So half of pi is about 1.57. Pi is about 3.14. So 2.3 radians has to be in between there somewhere. So that's that angle. Now for cosine, is that a positive quadrant or a negative quadrant?
Negative.
Good. For cosine, that's a negative quadrant. What's cosine's other negative quadrant?
3.
3. So our other angle has to be down here in quadrant 3. Such that those are symmetrical, or those are symmetric. Are you guys seeing some of the early importance of kind of being clear with which quadrants, which trig functions are positive and negative? That logic is going to come up a lot. How do we know where we are? Well, we know this is positive and that's negative, so we got to be in that quadrant. Okay, good. That anchors us. So keep playing with that logic. Now we could figure out what this little reference angle here is, but we know this angle here. What's that angle there?
Negative 2 pi or 2.3 pi
Not 2.3 pi, just 2.
radians.
Yeah, just 2.3 radians. Do be careful about that. That's something that's very, very common, is to start thinking about that pi like it's a unit instead of a value. Fair? So that is one of the reasons I chose just dealing with number or non-multiples of pi amounts of radians. Okay, so we could technically say that negative 2.3 radians is another angle such that the cosine values match, but negative 2.3 radians isn't in that first rotation. So we do have to do a little bit more here, because we essentially want this angle. How do you want to find that angle? Most of you guys
Subtract 4.6 from 2 pi or
Add the 2.3s.
well, you guys are making it overly complicated. What did you do with this 30 degrees? You subtracted it from the full 360, right? So can we do the same thing with this 2.3 radians? Subtract that off of a full rotation. Full rotation is 2 pi. Subtract the 2.3 radians. And that's going to give us that angle. If we want an exact value, that's an exact value. If we wanted to approximate it, 6.28, subtract 2.30. So what, 20, what, 3? would turn into a 1. It's a 5, so that's an 11. So that's a 7. Is that better? 3.72. So that other angle is 3.72 radians. It is a little bit easier at first to do it in degrees because, you know, we can kind of see and feel degrees a little bit better. We're adding and subtracting from something like 3060. The numbers are nicer, but the process in radians is exactly the same. It just feels weirder. But to find that 330, you took a full rotation and subtracted that little angle. What did we do over here? We took a full rotation and subtracted that angle. Just look worse. Again, this is going to come back a lot in our section on solving. So you guys happy with that? They're also nice questions at this stage, I think, because it makes us ask ourselves those questions. Okay, what quadrant do I have to be? It helps us kind of start putting all these things together, hopefully. Anything else that you want to look at from 6.3 or 4? If you're worried about 6.4, like, did we talk about 6.4? 6.4 is 3 and 6.4 are the circular and unit circular definitions. So we kind of did that together. So questions like, this is 6.4. Questions like, you know, if theta is pi, so what's the cosine of pi? What's the sine of pi? What's the tangent of pi? Those are all just on our circle, on our unit circle, on our unit circle, on our unit circle, on our unit circle. These are fun. If the sine is negative and the cosine is negative, what quadrant's that in? What quadrant is both sine and cosine negative?
Three.
3. So it is all stuff that we've talked about.
If you were to put the number 3 in there, would it be right? Or do you have to use the Roman numeral?
Probably. I would like to think so. Oh, it tells you here, input 1, 2, 3, or 4. It specifically tells you to use those inputs. So it's being picky.
That's
And
annoying.
frankly, I don't mind that. It's good practice, you know. That's the notation you'll see for quadrants like forever. So it's good. Okay. Here's another type of problem that I want to make sure you guys are happy with. Let's say, given that the sine of theta is equal to, what do I want here? How about negative 4/5? And the cosine of theta is greater than 0, so positive. Find cosine of theta, the tangent of theta, the cosecant of theta. Oops. To see, I promise. Essentially, if we know one of the trig functions and one of the other signs, plus or minus, we can find all of the other values on it. So the first thing, why are we being told here that the cosine is positive? Why do we need that? Well, we're told the sign is negative. Sign being negative tells us we are in which possible quadrants?
Three or four.
3 or 4, because those are the two quadrants where the y values are negative. But being told cosine is positive, cosine is only positive in which two quadrants?
1 and 4.
1 and 4. So what quadrant must this question be happening in?
4.
This question's got to be happening in 4. If we weren't told that the cosine was positive, we wouldn't know whether we're talking about a quadrant 3 or a quadrant 4 angle. We'd have to, account for both. We'd have to say, well, the answers are this if it's in quadrant 3, and the answers are this if it's in quadrant 4. We wouldn't know. Does that seem reasonable? Okay. So as with just about everything else, I'm going to push you guys to, whenever you do one of these kinds of problems, draw yourself a little circle. Ends up making a big difference after a while. So our angle is going to be somewhere in quadrant 4. Now I'm drawing it in a fairly arbitrary position. I don't know where it is. I'm just drawing an example angle in quadrant 4. But what do we know? We know that this y value is going to be -4 if that radial length, or that hypotenuse, if you want to think about it that way, is a 5. Right? We know the ratio between the y and the r, or opposite and hypotenuse, if you want to imagine it from the perspective of that little triangle. Now, frankly, it doesn't have to be the lengths -4 and 5. It could be anything with that same ratio. So this could be, say, -8, and that could be 10. Has the same ratio. One of them could be 1, and the other one could be 4/5 if you wanted to. Could have a, let that be 1, and then that height is -4/5 if you wanted to. Fifths, sorry. -4/5 if you wanted to. As long as that ratio holds, it's going to allow us to find the other trig functions for this angle. And it's usually handiest to use the whole numbers just for our own convenience. Now, if we want to know what the cosine is, or the tangent, or the secant, or the cotangent, we're going to need to figure out what that other side is, what that x value is there. If only we had some sort of tool for figuring out the third side of a little right triangle. Do we have such a tool?
Pythag. The
Pythag.
Pythag. Yeah.
Good. So that other side length, I'm going to go ahead and call it x squared plus the -4 squared equals 5 squared. So x squared plus 16 is 25. X squared equals 9. So x is equal to what?
3.
Square root of 9.
3.
Is it like positive or negative squared?
Plus or minus 3. Now,
Okay,
does
do we
the
have to
plus
do
or
that?
minus matter? If we were in quadrant 3 instead, we'd have to use that -3, right? The only reason we get to say, oh, it's just the +3 is because we know we're in quadrant 4. So if you said 3 because you went, oh, I know it's plus or minus, but I'm taking the positive version because I'm in quadrant 4, if that's why you said 3, yay. If there was any other reason you just said 3, boo.
I
Fair?
absolutely thought that all through.
Good. So because we know the quadrant, we get to assign which one it is. But as soon as we have that, what's the cosine of that, of an angle that makes that structure? Cosine is going to be our x over our r, or our adjacent over hypotenuse, whichever you want. Tangent's going to be the y over x. Cosecant's going to be the reciprocal of our sine, so we technically already had that one. Secant's going to be the reciprocal of our cosine. 5/3. And cotangent, the reciprocal of our tangent.
So if you didn't know what quadrant it was in, would you have two answers, a positive one and a negative one?
Yes. And like say it was in, like say if we didn't have this, we'd have to say, you know, if the cosine is less than 0, we have this answer. Sorry. Yeah, if it's cosine greater than 0, we have this answer. If the cosine was less than 0, we'd have, they wouldn't all be negative. That one would be negative. The tangent, they'd both be negative. In quadrant 4, tangent would be positive. The cosecant would stay negative. So you'd have to be careful, you know. So just thinking, oh, the signs switch. Only the things that have that 3 in it, only the things that have that adjacent length in it switch. The ones that don't switch. So you do have to be a little careful. Cool. So this is frankly a pretty common type of question. So much so, why don't I give you guys one to play with for a minute? Given, let's say, well, let's do that. All right. Given the tangent of theta is equal to negative, oh, how about 5/3? And how about the sine is negative, less than 0? Sometimes in these, you can be told things like tangent of theta is negative 5/3 in quadrant 4. So you could be told the quadrant directly. It's nice when that happens. We're being told the sign, whether the sign's positive or negative, to imply the quadrant as opposed to being directly told it. But given that, find the cosine of theta, find the sine of theta. So take a moment and find those. You can do one of them for you. We lost Victoria. Where'd she go? It's surprising. She always looks so happy. Sean, what was your first step?
Figuring out what quadrant it's in.
Okay. Once you had the quadrant, what'd you do?
I'm not sure yet.
I drew a circle.
That's what I was looking for, right? You and I have worked together enough. Sean, draw a diagram, draw a diagram, draw a diagram, right? I've had it happen quite often that, when I'm in class, particularly during, tests or quizzes, or when people are working on stuff, somebody will come up and say, I just can't figure out how to start this problem. I don't know what to do. I'll say, oh, where's your diagram? And they'll go, well, I haven't drawn a diagram, but I was wondering, go draw a diagram. And they'll go and they'll sit back down. A couple minutes later, they'll come back up, go, well, I tried this and this, and it's still not working. I'm like, but where's your diagram? You didn't go draw the diagram. They're like, well, yeah, but I was playing with this instead. It's like, well, go draw a diagram. They go, they sit down, they work for a little bit longer, come back up a couple minutes later, and I stop and I say, if there's not a diagram, I'm not talking to you. And they usually look kind of offended and go sit down, and I watch them. Usually within about 30 seconds, you'll see them go, they'll be drawing something, they'll go, oh, just draw the diagram. I can't tell you how many times I've had that exact series of exchanges happen. Draw a diagram. Sean, you remember my spiel about the brain, right? Largest
Yes.
single-use part of your brain is the visual cortex. The amount of information that the visual cortex is able to process is just unbelievable. But the part of your brain that does math is like this little tiny piece that it's really very, very small. How to get better? One of the ways to get better at math isn't to make that little math processor better. It's to make more connections between it and your visual cortex, as well as more connections between it and your language center, the second most powerful single-use part of your brain, depending on how you define single-use parts of brain. So yeah, every time you can connect your mathematics to that powerhouse visual cortex in the back of your head, man, you're helping you. All right, what quadrant's this in?
2.
Well, if the sign is negative, that means the y values are negative, right? Y values are negative in 3 and 4. Where's the tangent negative? You're right that the tangent is negative in quadrant 2, but where else is the tangent negative?
Quadrant 4.
Quadrant 4. So we got to be down here to 4. Does that make sense? So this negative 5/3, when we break that up into our y and our x, that y value has to be the negative value, and that x has to be the positive. If you were up in quadrant 2, that would switch, right? In quadrant 2, the 3 would have been negative and the 5 would have been positive. Fair? Again, that's why we got to make sure we're in the right place. To answer most of the rest of these, or the rest of these that aren't done yet, we're going to need that radius length or that hypotenuse length, whichever way you prefer to think about it. And of course, we're going to use Pythagorean theorem to do that. What's that? 9 plus 25 is r squared. So what, 34 is r squared? We still technically get a plus or minus the square root of 34. But because it's a radial length, we always take the positive values for radial lengths. You might notice I'm going to encourage you guys, whenever you solve these, put that plus or minus there. If you are not in that habit, you will forget it when you need it. But once we have those values, we can fill out all of these. What's the cosine going to be? Three square root of 34 over 34 after you rationalize it. Sine's going to be the negative 5 square root of 34 over 34 once it's rationalized. Secant's going to be the square root of 34 over 3. Negative square root of 34 over 5. Sorry, those are kind of squishy. For the cosecant, and we already had the cotangent. So there are not a lot of mechanics in this process. It really just comes down to knowing the implications of what you're told. Questions about that?
So why is the square root of 34 positive in this situation? I'm confused.
The radius value is always positive.
So when does the negative come in handy?
For radial lengths, they don't. For the x's and y's, they do. And at the end of the course, when we start dealing with polar coordinates, that distance from the origin can be negative. So it does come up later in applications. But since we knew we were finding a radius, from the very beginning, we knew it was going to be considered positive. I just want to make sure we're in the habit of solving it completely and correctly, and then using the positive version because we're making a choice, not because we're not keeping track of our plus and minus. That makes sense, Alec?
Yeah, that makes sense. I just got a little lost.
Yeah, there's still a lot to keep track of here. Okay, before I let you go, speaking of plus or minuses and square roots, we're going to, in a couple of days or early next week, start talking about inverse functions. And there's an issue that's going to come up with inverse functions that I want to make sure we're kind of prepared for. And one of the nice ways to prepare for that is to talk a little bit about square roots. So to do that, what hopefully should be a straightforward question, what is the square root of 16? I'd like everybody to answer that.
4.
Plus or minus 4.
So you didn't all give the same answer. Some of you said 4. Oops. Some of you said 4. And some of you said plus or minus 4. Those are different. So which one is it?
Plus or minus.
Okay, I've got one strong opinion for plus or minus. The square root is a function, right? Functions have one rule. To be a function, every input has to have one and only one output. Every question has to have one and only one answer. That is the fundamental definition of being a function. So if the square root is a function, how many answers is it allowed to have? 1. So I ask again, what is the square root of 16?
4.
It can only have one answer, and that answer is 4. So why do we get plus or minus when we do things like this? Well, that happens when we have our x squared equals 16. How do we solve x squared equals 16? What do we do mechanically?
Square root of both sides.
Perfect. So we take the square root of both sides. Great. Now, what's the square root of 16?
Plus or minus 4.
We just argued that, right? What is the square root of 16?
4.
You
4.
can see how ingrained that is in your thinking, though, right? You want it to be that plus or minus. It is not. The square root of 16 is 4, period. What is the square root of x squared?
X.
No.
Plus or minus X.
No.
Dang it.
So what's the square root of 5 squared? 5 squared is 25. Square root of 25 is 5, right? That makes it look like x becomes x. What about the square root of, say 10 squared? That's the square root of 100, and the square root of 100 is 10. You got your 10 back, right? Again, that makes it look like the square root of x squared should be x. But what's the square root of -3 squared? What's -3 squared?
No.
9. What's the square root of 9?
No.
3.
Did you get back your input? What did you get back?
The opposite of your input.
Technically, I'm going to say the absolute value of your input. You're correct. It is the opposite of the additive, opposite of our input, but only when it's negative do we get the opposite. When it's positive, we just get the input. And that's our kind of definition of what absolute value is. Leave it alone if it's positive, switch it if it's negative, right? What values for x solve the absolute value of x equaling 4? Well, that's true when x is equal to 4 and when x is equal to -4. Why is this important? Well, you can go through a lot of mathematics and never realize this, as a lot of people do. But the plus or minus is not coming from us taking the square root of that 16. The square root of 16 is 4, period. The plus or minus is coming from that square root of x squared. And the reason for that is if you look at x squared, That's the graph of y equals x squared, right? What does the graph of the square root of x look like? Looks like that, right? The square root is only operating on part of the x squared function. So the square root isn't a complete inverse of x squared. So they don't simply undo each other. They undo each other with some mess left behind. Fair? Why do we have to do that? Well, if we didn't, if we said, let's make the whole inverse, that whole inverse wouldn't be a function anymore, right? So we have to restrict x squared to make it invertible, and that causes problems. This is going to happen with all of our trig functions as well. Our inverse trig functions are going to be restricted. So when we find just, our inverse trig functions of particular values, we're only going to get one answer, and it's going to be the one answer within our restriction. But when we go to solve, we're going to have to undo that restriction and pay the price for it. So I want you to kind of keep this example in mind. This is probably a way of thinking about square roots, and particularly solving square roots that you're not used to, with that whole absolute value thing in there. But it's a way of thinking about it that's going to be really helpful for us as we go on. Questions about that? Is that neat? You got to find these things neat or they just become frustrating, really. Okay. Anything I can do for you guys before you trundle off today? I do want to make sure over the weekend you guys start looking at and reading 6.5, because we need to do 6.5 and 6.6 next week. And I want to make sure we are able to kind of hit the ground hard on those. So start looking over, get the 6.4 stuff done, and then start looking over 6.5 so we make sure we can talk about that nice and smoothly. Okay.
So we need to do our homework through 6.4 and read 6.5 before Monday.
Yes.
Okay.
All right. Then I'll let you guys go, and I will see you on Monday. If you need anything over the weekend, send me a message. Let me know.